All right, let's look at FRQ number 3 of the 2024 AP Physics 1 exam. This is Form O. If there's any corrections, I will put it in a pinned comment below. So left-handed, a uniform beam of mass M and length L is attached to a wall by a hinge. Shown in figure 1, let one end of the string with negligible mass is attached to the right end of the beam. The other end of the string is attached to the wall at the hinge at point 1. The beam remains horizontal. The hinge exerts a force on the beam magnitude FH, and the angle between the beam and the string is theta 1. Theta equals theta 1. Represent, draw and label forces, not components exerted on the beam. Draw a force as a distinct arrow starting on. Okay, so this is a uniform beam of mass M. So we always start with gravity. So gravity M. One end of the string, negligible mass. Okay, so we just have this beam here. So then what's touching it? Well, we have the string here. That's going to be at an angle. So that we'll call it FT. And that is we don't have to draw the angle in there, but it's angle theta 1 there. And then what else is touching is a hinge. Now the hinge has an X and Y component force. It could maybe helping the string pull it up. You don't know, but like it could be upward, but it definitely has to have a rightward component to counteract the leftward force from the tension. So it's going to have some component. And you don't know the angle of this thing. This is not the same angle as this one. It's really important to recognize. This is a normal force, but it's like a circle, so it can point in any direction ultimately. And nothing else is touching it, so that's everything in the free body diagram. The string is attached on the lower wall, point 2, and the beam remains horizontal, shown in the figure 2. The angle between the beam is theta 2. The dashed line represents the string, shown in figure 1. The magnitude of the tension of the string is FT1. The magnitude of the tension of the string, shown as FT2. Indicate which of the following correctly compares FT2 to FT1. Briefly justify your answer using qualitative reasoning beyond referencing equations. So what do we want to talk about here? So there's two principles that we're going to engage in when we're doing this here. Is the net torque is to be 0. So I would look at it from a torque point of view, because the hinge force is sort of a reactive force. As we change the angle, the hinge force is going to vary. So we're going to make the axis of rotation the hinge, so I don't have to worry about the torque from the hinge itself. And we know the angular acceleration is 0. So in order for this to just remain suspended, the net torque has to be 0. Which means only the vertical component, because if I draw my R vector to here, only the vertical component of the tension force contributes to the torque. Now, the mg torque doesn't change when I change the force location. I change this angle, mg doesn't change, but the amount of the amount of torque that gravity does doesn't change, but the amount of torque that this has to do has to still remain the same to counteract the torque from gravity. That means the vertical component has to remain the same, because only the vertical component of the force relative to the R vector is going to contribute to the torque. But because it's at a steeper angle, that means the overall force has to be, like, the vertical component of the force has to remain the same for the tension between the two. But because at a smaller angle, that means the hypotenuse is going to be longer, right? Like, I need more magnitude because it's at a steeper angle like that. So therefore, FT2 is going to have to be greater than FT1. And I would say the torque from tension must balance the torque from gravity. And that implies that the vertical component of the tension of FT1 and FT2 are equal, but FT2 has a smaller angle. So the magnitude is greater. You probably had more room to write this out on your paper, but okay. Starting with Newton's second law of rotational form, derive an expression for the magnitude and tension in the string. Expression in terms of m, theta, and physical constants. They didn't say theta 1, they said theta, so we'll just keep as theta, which makes sense. So net torque equals I alpha. In terms of the principle, you identify your axis of rotation, you draw your R vector from the axis of rotation to where the force is applied for every torque. So the hinge doesn't exert a torque. This exerts a clockwise torque. So we'll say maybe clockwise is the positive direction, counterclockwise negative. Honestly, it does not matter, especially because the net torque is 0. So this is a positive torque based on my sign convention for direction, because pulling down here would cause it to move clockwise, and that's going to be L over 2, and it's already at a right angle. So that's L over 2, mg sine mg. And then the tension does a torque, and the vertical component of the tension is upward. So this is Ft sine theta, because remember this angle here is theta. So Ft sine theta, and then the R vector for that guy is from here to here. Okay, so that's L. So that means Ft sine theta is the vertical component compared to that R vector. So it's going to be minus L times Ft sine theta has to equal 0 because this thing is no angular acceleration. So then you can move this over, and you'll see the L's cancel. So then Ft is going to be mg over 2 sine theta. That. Okay. Move that over, and then divide by sine theta. Okay, I think that's right. Okay, is your derived equation consistent with your justification in part B? Explain your reasoning. Okay, so if theta is smaller, then sine theta decreases. Because it's inversely proportional, and Ft is inversely proportional to sine theta, that implies Ft increases. And then answer the question. So yes, it is consistent. Okay. The string is cut and the beam begins to rotate about the hinge with negligible friction. On the following axes, sketch the angular speed, which means we don't care if it's positive or negative, as a function of time for the interval while the beam falls, but before the beam becomes vertical. Now, this one's probably the trickier part of this. So initially, you're going to have some angular acceleration. However, because you're only going to have torque due to gravity. However, the torque due to gravity is going to decrease over time, because as the angle changes, right, then what's going to happen is the torque is now not going to be mg times L over 2. There's just going to be a smaller component here. So you should start off with no angular speed. It's going to and then remember the slope is going to be the angular acceleration, right? Angular speed versus time. So you're going to have the most acceleration here, and then it's going to kind of level off before it becomes vertical. So once it's vertical, then the torque will be 0, right? Because if I do my axis of rotation here, and I have gravity, so once it's vertical, I should expect the torque to be 0, because then, right, my R vector is going to be parallel to mg, and so it's not going to have a torque. So it's going to increase, and then you probably just need to make it concave, and just don't make it go down or negative, and don't make it horizontal because it's before the beam becomes vertical. If you made it slightly horizontal right at that point, it's probably fine, but it should just always have some torque, but it should be a decreasing acceleration over time because the torque decreases over time. But the rotational inertia doesn't change. Okay, and so that is FRQ number 3.